All right, so we are going to get started with our seminar, and generally Victor does this introduction, but I'm going to do it today. So, welcome to the Data Science Seminar Series at the University of San Francisco, sponsored by the Data Institute. The Data Institute is the umbrella organization for all the things data science at the University of San Francisco. Our speaker today is Dr. Beinan Wang, a senior staff software engineer at Luxio, and he is also a technical steering committee member for PrestoDB. Prior to Luxio, he was the technical lead of the Presto team at Twitter, and he built large-scale distributed SQL systems for Twitter's data platform. He has 12 years of experience working on performance optimization, distributed caching, and volume data processing. He received his PhD in computer engineering from Syracuse University on the symbolic model checking and runtime verification of distributed systems. Today's talk, he's going to talk about data access patterns in AI and analytic domains based on practical experience with large-scale systems in open source. He will also discuss the evaluation results of various caching strategies for AI and analytics and provide caching recommendations for different use cases. Let's give a big applause for Dr. Wang here.
Thank you. Thank you everyone for joining the seminar. Today I will share something we just learned from industry. We call it data access pattern. We believe it's super important if you really want to define some big data infra. Also, if you want to improve the efficiency of your data pipeline. Yeah. So the content I will share today is mostly from the. It's a big room. Yeah, I have never been such a big classroom for a while. I think it's almost 10 years ago when I was still a teaching assistant. I have something like this. It's a big room. A lot of students come in. We have some lab works to share some code in the session. But today is probably something different. We will share something we learned from the industry rather than from a textbook. Okay. But firstly, I start from the caching. Why we need a cache? Just because sometimes we think the storage of the server or whatever the disk or maybe the memory which contains your data is not fast enough. So we want to put something faster than your normal storage in the middle, which means when you want to fetch some data from the storage, you check the cache first. If it's in the cache, you will get the data from the cache with a much faster speed. If it's not there, we fetch the data from the storage. This is the very common pattern. It's for the read path. For the write path, that might be a little bit different, but I will cover detail maybe later. So here's the thing. If you want to improve the efficiency, you need to improve the cache hit rate. Am I right? Because the cache storage is faster, it should be more expensive. You cannot put everything into a cache. So which means we need to think about it. We should put the most valuable data in the cache rather than everything. But how can we figure out what kind of data is the most valuable? We should know the traffic pattern, or we should know how the cache works right now. Who is using the cache? How is the purpose, and what's the process with the cache? The thing is, we really have very little cache in the industry. We have client-side cache, we have a load balancer cache, we have CPU cache. You all have a laptop, right? The chip, the CPU chip in your laptop, they have built-in cache. But of course, the capacity there is very small. But if you're talking about big data, you can have something like a Luxio. You can have terabyte level of capacity. Maybe it's 1,000 bigger than your cache in your laptop. And as I mentioned, Luxio is the I'm not starting Alexa today. I'm just using Alexa as an example in my session. So Alexa is, as I mentioned, it's a cache for the big data. Because I'm using most of you are in the data science or computer science major, am I right? So when we talk about the machine learning, when we talk about the data science, we're talking about the distributed system. Mostly, nowadays, we will have a super huge data set. The traditional cache, something like Memcache, like Redis, it might be not big enough for our data. So then we have a Alexa. You can put a Alexa in the middle, and you can have all this kind of storage. You can have S3, HDFS, whatever, NetApps. You can have whatever the size is, but it can be very big, can be very small. Then all of your computer engine, something like Presto, I'm working on Presto for a while, and also something like MapReduce, something like Hive, and also your machine learning engines like PyTorch, like TensorFlow, they can access the data from Alexa. Right? But again, Alexa is faster than any other storage, but the thing is, Alexa will probably be more expensive. The same thing, you cannot put everything into the Alexa. But if you really want to improve the efficiency of your data accessing, we should think about it, data pattern. As I mentioned, today I will share something from the industry. So I will also use Uber's tech stack as an example, because Alexa team is working closely with Uber's data infra and the machine learning team. I think it's very typical, but probably Uber will be more complicated than any other company because they prefer to use open source tech stack rather than to buy a bundle from Snowflake, from Databricks. See, Uber built everything by themselves. They got some open source things like Kafka, like Alexa, like Parquet, like Hoodie, like Hadoop. They put out everything together and connect them together from scratch and to make it connected to process their workload. Okay, the point here is do you want to make a storage engine, or maybe you also want to make a computer engine? The challenge here is you will facing multiple technologies, tech stacks. You will facing different traffic patterns. Am I right? Because sometimes this may be from the real-time service from the outside. Sometimes it's maybe from the internal offline traffic, something like a Presto query, something like a MapReduce job. Sometimes it might be difficult to fit in your product into such a big infra. But today I will more focus on the big data part. I mean, just here. It's still a lot, but I will try to make my session more focused on the traffic pattern and the session to be here, because I think that's the most related part to our work, and also I think that's also the things more close to the data scientist and the AI workload. Okay, let's go to the real topic today. What's the data access pattern? The thing is, when we have some data you want to access, probably you want to read some data from a file. The pattern will be very different. Sometimes you may do something like read only. Right? If you are running some machine learning training job, mostly you won't change the training data, right? You load the raw data from the remote and do some training job. But when you finish your training, you want to write some checkpoint, some model you trained. Probably in this case, it's write only. Right? So during the different stage, you may have different type of access. Probably just read, probably maybe write. Sometimes maybe you combine the read and write together. And also, for the same file, Sometimes, for something like a large video or image file, it highly depends on your algorithm. Sometimes you may do the sequential read, which means you start from the very beginning, you keep reading until you read the end. They may call it sequential read. The other thing is if you have some structured data like a parquet, your algorithm may got some ideas, which means you may have a filter, something like if we have a database, something contain all the students in San Francisco, but if we just want to filter out the student in this class, we have 80 or 90 students in this class, which means we don't have to touch everything in your data. So in this case, we may change our algorithm based on the index of our data. We selectively pick some data in the large file. So in this case, we might see random data access pattern. It's not really random, it's still based on your algorithm, but from the storage perspective, because the storage know nothing about your algorithm in the computer part. So from the storage, it looks like it's random data access. It maybe start from the very end and then seek back to the front. Maybe start from the front, but it escape a lot of rows or lines in your data file. Obviously, for this two data pattern, we need different data access strategies. Am I right? So if we have sequential read, probably the best optimization here is we can prefetch the data because we know you need everything in this file. So when you read start from the beginning, I can have some background thread or something else to keep prefetch the data from the file. But if you have random data, the prefetch may not work because you don't need everything. You just need maybe a very small portion of your data. If you prefetch, you load everything from your data storage, which means you have the we call read amplification. It will slow down your data access, and also it will give you a much higher cost because currently, I think the majority of our customer is using the storage on cloud. The storage on cloud means they're charging you by the number of API calls, but the number of the bytes you transferred. Anyway, they charge you in many different ways. So, but if we're talking about the read application, which means if you read more, it will charge you more. So if we're talking about the optimization here, we really need to focus on the traffic pattern to provide the most efficient way to read the data. And for the third column is the file size, definitely, because now I think it's maybe talking about 10 years, 5 years ago, we can just focus on something like a parquet file, like a CSV file. They may have the unified the size, something like a parquet. Mostly they use 2 block or 4 block of the HDFI. Mostly it's 500 gigabytes or 1 terabytes. But nowadays we have machine learning load, we have the computer vision, we have large language model. Very likely you have everything in your data lake. So the size of each file can be very small, can be just less than 100 terabytes. Sometimes I even see some of our users, they are training with some image file with just 1 byte. I don't know how it works, but it's just there. 1 byte image file. They load a lot with 1 byte image file from their database or whatever and start training. But the large file is still there. If you are talking about a large language model, they may load some error file from remote. It can be very huge. It can be 10 terabytes or 100 terabytes. Some large internet company, they are using super large Apache error file. It can be more than 10 terabytes. And also, because I'm working in computer science, working as a backend engineer, the SRA, or you can say the requirement, will probably be different. Some of our surveys, we are more care about the throughput. Mostly talking about the data process pipeline, talking about the AI pipeline, we may more care about the throughput. But sometimes we may more care about the latency. I mean, probably maybe the end-to-end latency or maybe the latency per request. So for different workload, for different customer, they may give their own requirement. So that's why we have a Luxo here. We want to design a Luxo to be more adaptive to all of this kind of traffic pattern, the type of stuff like flow, the file side, and also requirement. So here's just some more background. I will spend more time about the background in today's session because I really want to be on the same page. We know the same pain point in the industry. Here's the machine learning pipeline. You can see they have several stuff from the data ingestion, from the data preprocessing, model training. For each step, they may have their own needs, requirements, data access pattern, files they need. They're probably very different. And then, as I mentioned, they have multiple data access patterns. So what's the real challenge? What's the real challenge in the data loading? First challenge is, okay, let's put it this way. So if you only have 10 terabytes or maybe 1 million bytes, whatever, small data volume, no one cares. No one cares about data pattern. You can just load everything into a laptop in one time and keep it somewhere. It doesn't matter. But the thing is, we're talking about something really happened in the industry. We are talking their production data and production traffic. You cannot put everything into a laptop. Then that's something becomes real messy. Even you have high-perform server, which can still not able to put everything into this server. So we need something more sharded, more decentralized data storage. And you need to load the data maybe from everywhere, from maybe thousands of servers, maybe from another data center. Actually, that's a real case in Uber and also in Twitter. Uber and Twitter, they have their own data center. In their data center, they already have more than 1 million servers running there. But it's still not good enough. Because they have more and more data need to store put into their storage. So we are suffering from what we call the capacity issue. We need more machines. We need more machines in our own data center. But the thing is, we don't have area. We don't have power. So the hardware team reject us to put more machines in our data center. So in this case, we are starting using the cloud storage because the cloud storage can be deployed by Google, whatever. They can spread the data to everywhere. They can have dozens of data centers running in this world, so they can load the data from there. Then we can have almost unlimited capacity. But again, still some limitation. But the volume can be, the capacity can be much larger than our own data center. But again, if we use cloud storage, which means you need to load data from remote, the bandwidth, the latency will be much higher. There's a lot of trade-off here, just because we really need a large data volume. And also, as I mentioned, if you want to improve data capacity, you may suffer from the remote data loading issue. You cannot always load data from your local machine or from your local data center. And then also, as I mentioned in my previous sections, the data pattern will be very diversified. Again, if your data volume is small, it doesn't matter. But if you have a large data to load, we really need to care about the data pattern. Here's some research we did before. There's the trend of the data is not in the cloud storage. I don't know how much it really is, but I just know there's so many zeros in this number. So if we are talking about dealing with such a large data volume on the cloud, it will be a challenge. And here I would like to share about the most typical architecture we learned from the modern internet companies from Meta, from Uber, from TikTok, they all use such a architecture to do the machine learning jobs. Just because, as I mentioned, they really have a very large data set, so they cannot put their training data just in one data center. Probably they may have some data stored in some remote storage or cloud, maybe on another data center. But the thing is, for each data center, they may have their own compute power. So they may have some maybe 1,000 GPU machine in the East Coast, but their data is still in the West Coast. So they need to load the data, the training data from the remote. And also, when they finish the training, they would like to write the model back into the cloud storage or maybe a remote HDFS. And on the other side, as I mentioned, they have multiple data centers. Each data center may have their own compute power. If they want to do the inference, they have to load the data. From the remote. Am I right? Some internet company like TikTok, like Uber, they have more than 10,000 machines. They do the inference at the same time, which means if you got a new model there, 10,000 machines. Want this new trained model from a remote storage as soon as possible. So the latency, the throughput requirement here should be very, very high. It's even higher than the training part. Here is a table made from my teammate Hope. She collected all the data pattern and the different requirements for each stage of machine learning training and inference and deployment. I don't want to go through every detail here. You can just see it's almost very different for each stage. For some stage they need high throughput, some stage they may require low latency. They are very different. If we focus on the machine training part, you can see the different algorithms like the computer vision, like the NLP. They also have very different access pattern. Like the computer vision, they may have sequential read of small files, but on the NLP mostly they have random read, 4K random read on a large file. Okay, so based on the traffic pattern and the challenge we learned from the industry, we are thinking, in this case, because your remote storage, like the cloud storage, also probably a local storage like HDFS, probably they cannot handle so many access pattern in your machine learning training. So they are trying to make a cache to improve the data access performance, and also we can reduce the requirement to your storage engine, because the storage engine actually they're designed for large capacity. They are not designed for really designed for the data locality and high performance data access. Which means if we have something running, it can be machine learning, it can be analytics workload running in your local data center, we can put a cache. We can put a cache just very close to your computer engines, and your computer engine can just access our data cache. It can give you a much faster data access instead to access the storage, access the remote storage. And also, as I mentioned, because your cloud storage is something, it will charge you by the number of API calls, and also charge you by the bytes, how many bytes you transferred from the remote. So in this case, if you can have a cache, you have a local cache in your local data center, your local computer, it can reduce the traffic, both API call and the egress, the data transfer from the remote storage. So this slide just shows why we need data locality, why we want to put the data in the local rather than in the remote. So we're talking about the data locality solutions. There's three typical solutions. The first one, I think it's used a lot for the machine learning engineers. For every time they want to train a model, they just copy the data. They just copy the data from remote, from S3 to your local desktop, or maybe to your GPU training node. The second one is you can have a cache. You can have a cache, let me say the first one is that we just read the data from without any cache, without anything. We just read the data from the remote storage on the fly. The second one, we copy the data to the local before the training. And the third one is we push a caching layer in the middle for data reuse, which means you don't need to handle the data copy. You access the data from the cache. If it's there, we use the data in the cache. If it's not there, we ask the cache to load the data from remote. So here's some number we got from the. It's an in-house testing. It's not the real production case, but I think it can show the same thing. So which means this one is real data from the remote on the fly. So it's a ResNet 50, I think. If you load the data always from the remote, you can see the data loading. So here is the data loader. The data loader will take you more than 80% of the time. So the purple one is the data loader. It's 82% of time will be consumed by the data loading. So what does that mean? Which means your very expensive GPU is just waiting there. It's just waiting for your data loading. Right? And more than 80% of time is waiting. So if we can fix that, we can improve the utilization of our GPU at least 5 times. Am I right? So to fix that, someone figured out, okay, if the load data from remote is slow, we can copy the data. Before the training, we can copy the data from remote to local. Am I right? So, okay. Yeah, so some machine learning engineers or infra engineers, they want to fix the remote data loading issue. They suggest before the training. This actually this approach is on the textbook of the PyTorch. They are asking the users to always copy the data from the S3 to local before training. But the thing is, your local disk, the capacity for local disk is very limited. Am I right? As I mentioned, the data set becomes larger and larger. They have so many zeros there. So if you're talking about the real production traffic in the internet companies, mostly you cannot put the data from remote into local. And also, even though you have a large server with 10 or 20 SSD connected there, it's still a trouble that because when you copy the data from remote to local disk, after your training, you need to delete your data. Am I right? And also for some security reason, for the data privacy reason, some internet company like Uber, like Twitter, like Meta, they have some enforcement, which means you cannot put the production data into a local. It's not possible. So you cannot do that. So in this case, we are thinking we can use something we call a local cache, which means we are using a local disk as a cache, which means this one can handle the data migration, copy. You don't need really to delete the data. After you use you put some new data into the cache, the old data will get evicted somehow. But the same thing, the capacity is still an issue there. Because, as I mentioned, the data set will be very, very huge. So here's the S3 FS building local cache. I know you are a student in this major, so maybe you can take a try. It's very easy to set up. If you are using some data from S3, you can just set up this one by using the S3 client or using the S3 feed. We can mount a local disk as your cache, and you can map the data from a remote S3, just something like a local folder. Both S3 fields and the Luxio field SDK, they provide the same feature. But again, the data, the capacity will be very limited. So if the local cache is not fully fitting the machine learning pipeline, so we are thinking if we can make a decentralized cache, we can use the disk from all of your remote servers, because in your data center, probably you already have thousands of servers there. If we can reuse their disk to construct or to make a decentralized cache, and your data from a remote, maybe from the cloud storage, can spread to the spare disk on your servers, probably we can fix the issue. So Luxio just released, we call the Luxio 3 XXL, it's the open source version. We have open source, we also have the commercial version. We implement a decentralized cache for the big data storage. We can provide a high scalabilities. We can store. Actually, it's much larger now. It's one worker supports 30 or 50 million files. Which means if you have 2,000, maybe that's 200 worker cluster, you can support billions of files. And also, if you make something local, if your disk is corrupted or maybe you restart or something, you may lose your data. But if you're using distributed solutions, you can have 99.99 uptime. It's super important for the internet company for their data infra. It might be more technical detail things, but the thing is, by using a Luxio, we can think in this way. We are mounting your remote data into a local folder. It's more like a virtual storage, something like a Dropbox. Do you still use the Dropbox? I think it is quite old, but anyway, it's still there. So which means you can have a larger capacity. You can have a much larger disk. Looks like a disk, but actually not. All the data in the cache tree is from a remote machine. So in this case, your training node, we call the application pod here. They mount a persistent volume, and they connect to the field power. So it looks like the field will make itself just looks like a local disk folder. And if you have some data access, the field will help you to fetch the data from the cache. If it's not in the cache, it will also help you to fetch the data from the real remote storage, the data on the cloud. So here is some performance benchmark we are using for the single worker. As I mentioned, probably you can have hundreds of workers there, so the throughput, the aggregated throughput can be super high. You can see we have really good multi-thread performance because this one is running in the AWS EC2. For each worker, the throughput of each disk is very low. It's just 250. We are using very slow disk quality. So which means by using this one, we can make our cache, the decentralized cache, running the speed and the throughput is very close to a local disk. Because the hard limitation, as I mentioned, is 250 megabytes per second. This is fast, not fast. So it's okay. It's actually mostly for the normal setup. It's the hard limitation here. And also I'm not selling Alexio. I'm just want to show the difference. It's open source version. You can download the Alexio from the GitHub or GitHub. So you can see it's talking about the computation training load. The Alexio field can have a much higher IOPS. The IOPS here means the IO operation per second. So why we compare the IOPS for the data training, for the CPU computation training, just because for most computation, they are reading from very small image file. So which means the throughput here is not strictly important. For the most computation training work, we need to load as many files as we can. Because each file is very small, just 100K or maybe less than that. So we're talking about IOPS. So if higher IOPS means better performance, means you can finish your computation training job faster. On the other side, it's the ALP training workload. As I mentioned, for the ALP training load, they are loaded the data from very large data file. They can be sequential read, but mostly it's the random read. So in this case, because they need to load the large data from remote, we are talking about the throughput. So here the IOPS is not so important. The throughput could be very critical to this kind of work. We can also see by using okay, here's the tricky part. The Alexio Fuse is provide the POSIX API, which means they can mount the data just like a local folder. But we can see for the field in the POSIX API, the POSIX is just an interface for the Linux files. It looks like something like if you're using the terminal CP, ROS, it's POSIX API. We call it POSIX API. But we can see for the POSIX API, the throughput is just, I think it's less than 50% using the RESTful API, the Alexio S3 API. Just because the fields, I want to go a little bit deeper here. I know most of you maybe want to work on the Linux kernel, but the thing is, because the fields they are using some data communication, a single thread data communication between the Linux kernel and the user space. That's the bottleneck. That's why we are seeing using looks like more heavy protocol like the RESTful API, like the S3 API, can get a better performance. I show I'm showing this kind of chart, not selling Alexio. I just want to talk for different data patterns, different API or different design can give you very different performance. So that's why we should think about the traffic pattern first. We should know the traffic pattern from a running system and select right API. Because it's also true for the computation, because here we are loading the very small files. You can see the S3 API. Because in this case, the throughput doesn't matter. The S3 API mostly can give you very throughput, but for latency, for the IOPS and concurrency, that might be very, very bad. Because for each request, you need to make a very heavy hacking and do the very heavy communication between the your server and the S3 server. So that's why different API, different algorithm can give you different performance gain. And you can see on the other side, on the ARP, the S3 can give you a much better performance. Because here we measure the throughput, and on the other side, we measure the latency and LLPS. They are very different. Okay, so then I will share some real use case study from the industry. They are working with the Microsoft, Shopee, Zhihu, and others. So I may already shared something similar in that previous section, but the thing here is for the large language model, you can see the. I just want to go deeper here. You can see for different stage, they may have their different concerns. For the training on the very left, because here the GPU, they are mostly using GPU as the training compute power, so they suffered from the GPU utilization. There can be multiple reasons, but one of them is the data loading. So if the GPU is waiting for data loading, you may see the low GPU utilization. And on the other side, for the offline cloud, they are doing something like the model training on Spark. Because they may have thousands of nodes reading the same file at the same time, they may overload the storage. We got a lot of complaint from the HDFS team because the HDFS is not designed for this kind of traffic. So if there's a lot of running jobs there, they fetch the same data. Because HDFS, they are more designed for the durability of your data. They persist your data. They make each data as 3 copies, but it's not a cache. So if you have thousands of machines to read the same data, it will complain. You need more replication or something to fix the issue. And then for your online training, as I already mentioned, you may have thousands of inference machines. They may load the same model from remote. Because it's not in the same data center, you may see the network congestion. Because the bandwidth between the different data center, they are very limited for most companies. They are very limited. It is super expensive. So mostly we won't just load the data from another data center directly. It will cause the issue. We may run some offline job to copy the data. But again, if we're talking about the model inference, because the model inference server, they really want to get the newest model as soon as possible. So there might be some conflict here. Okay, so to fix the issue in the previous slides, that's the real issue we got from Uber and Zhihu. So we put a Lexio cluster in every data center. So the training will load data from Lexio to speed up the data loading to increase the GPU utilization. For the offline training works, they also put Lexio the same thing. It can reduce the load of HDF. So for here, we are not really designed for the performance. We designed to protect the storage. So which means if you have thousands nodes to fetch the same node, fetch the data from the same node, you will see a huge spike. So with the Lexio, the spike will go to the Lexio because Lexio is a cache, and which means the Lexio only load the hot data once from the HDFS. For the other requests, they will just load data from the Lexio. It can eliminate the spike from the real storage. And on the online cloud, we also put a Lexio. For this one, we use a Lexio to load the data from remote, which means all of your inference server, they won't load the data on the fly from remote data center. They load data from Lexio. Alexu will handle the model update. So when you got a new model, it will notify the Alexu, okay, we have something new. The Alexu will try to update the model file they cached and serve the invariant server. Okay. Here is the GPU utilization without Alexu, I think. So you can see, as I mentioned, 80% time spent on data loading, and the GPU utilization is very low. It's less than 20%. And by using Alexu, you can see the GPU utilization increased to 93%, just because we reduce the time spent in the data loading. See? By using Alexu, you can use any cache. I'm not selling Alexu. You can use any cache, but the same thing, which means load data from the cache and the time spent in the data loading is just 1%, which means we do nothing. We do nothing, just improve the efficiency of I/O, which can 5 times increase the efficiency of your GPU utilization. Super easy. Because many machine learning engineers, they want to change the model to improve the algorithms. Sometimes they got a good result, sometimes they cannot. But by using this one, it's super easy, right? It's not very expensive, and put a cache in the middle, you can get the same thing. Here is the previous one talking about the model training. This one is talking about the model deployment. You can see after the most left part is it's no Alexu. You can see the specs, the latency specs is super high. Sometimes you can get some good result, but sometimes it's really bad because it's tail latency, which means maybe 50% of your request is okay. It can be finished in 5 minutes or something. But there's still a lot of requests. Maybe 10% or 5% of your request is super slow. It can be longer than 20 minutes. That causes the issue, which means some of the machine cannot get the newest model on time. So if the model is for something like ads, like for the recommendations, if you get a late model, which means it maybe have some negative impact on your revenue because you cannot push the most recent content, the most valuable content, and on-time content to your customer. And you can see by using the Alexu, and also you can see using the Alexu S3 API, and we are optimize this process to be more smooth, lower latency, and less specs, no surprise. You can always get your newest model file on time. Here's another case study from Zhihu. They are doing the very similar things. They put the Alexu on their each data center. Each data center have their own Alexu. They may have different setups. They improve their GPU utilization from 50% to 93%. Why is always 93%? It looks like a fake number, but but it's just something like this. Yeah, I think I got almost everything. I missed something. But anyway, okay, so probably our market number delete some slide from my, because there may be some credential things there. I also would like to share something about the Microsoft. Okay, doesn't matter. It looks like it's still a secret. Okay, so any questions about Alexu? About anything? Data infra? Everyone say okay. We still have 10 minutes, I guess.
First, thank you for the
operationally treating the cache in the machine learning pipeline. So I heard that we use cache in the computer, like the memory can be cached over the secondary data storage. But it's the first time that I heard that using cache for machine learning pipeline and in purpose to use in the machine learning. But the question is like you explained the three methods that we use to increase the locality, and the first one is just using remote storage, but second one is using local copy the data from remote storage to local storage, and the third one is the Alexius. But what is the difference from copying the data from remote to the local and using the local cache? Because both of them I think use anyway copy from data from remote storage if on demand, so we can use that training data or whatever data multiple times if needed. But can you explain what is the difference between them, the two methods?
That's really a good question. The first one is we're talking about not the first one. We're talking about we manually copy the data from remote, am I right, to a local disk and then start training. And the other is using a local cache, using a local disk as a cache to serve the same thing. Firstly, if we're just talking about performance, probably there's no much difference. There might be some minor difference. The cache there may be some optimization there, but mostly it's still the same thing. We are loading the data from a local. The difference here is the first one is the security reason, because if you copy your production data from your real storage like HDFS or S3 from the local disk, for most internet companies, they have some regulation. You cannot copy the data, the raw data, from the data center to the local disk. But by using a cache, because it's not raw data, you can do some encryptions. You can have something to protect the data, which means without some credentials, others cannot access the data. So it's more secure. The first thing. Now the other thing is we always copy the data. It's not talking about a laptop. We are talking about some server, some running server. I mean, it can be shared by multiple users. All right. So which means if you and they are using the same server, maybe you copy your own data, I copy my own data, which means we are sharing the disk, am I right? So sometimes I might forget to delete my data, which means it's always there. And then maybe you don't have enough capacity. So by using the cache, mostly the cache will give you something called eviction, which means when the space is full, it can start evict my data because I'm not using it. We can use something like a FIFO, first in, first out. We can use something called RRU. We can, based on this algorithm, the cold data, the data is not that frequently used by the user, can be evicted. So they give you a management of your data. That's the benefit of using a local cache.
Yeah, thank you. And can I ask you one more question?
Sure.
So so you said that we use cache to reuse the data. If some data, the part of data can are used frequently, then but which part of the data we selectively store to the cache? Because in my perspective, we use all the training data, so I cannot tell which part is important or not.
That's a very challenging question for cache. I know that. That's why we are difficult. That's why we have our commercial version. Because just as you mentioned, it's not so easy to decide which one we need to cache. But I can start from the most common case. The most common case is we are training your model with multiple epochs, which means you will treat your model again. I mean, start from very beginning to the very end. Maybe the load data from very beginning to the very end, again and again. So by using the cache, the data in the cache can be reduced for each element. That's the first thing, right? But as I mentioned, probably the cache capacity is not big enough, which means we cannot put everything in the cache. Okay. The free solution, I mean, we have open source version. The open source version is we shut down the eviction, which means you only keep maybe the 10% of data in the cache and we speed up this portion. For other, so because it's not in the cache, you load from the remote. But for the commercial versions, we can do something like the data rotation, which means when you consume the first 10%, we are trying to prefetch the second portion and then the third portion, something like that. And also, because sometimes we have no idea what your training job, we have something we call the cuckoo filter, which means we have some metadata for each block. We have some stats to see which part is the most valuable for cache. Because it's shared, it's not just for you, it's also for others. So we need something to statistically know, okay, which one is the most valuable part to cache.
Thank you.
So especially in the cases where we maybe have data spread across multiple data centers and the computation or inference is being performed in one region or data is elsewhere, how much of an effect does network latency have on the speed of retrieval? And would you sort of place this caching node closer to where your compute is, so it prefetches to somewhere very close to compute, or is there an intermediary step along that way?
Both works, I believe. That highly depends on your SLA. It depends on requirements. In some cases, they are very sensitive to the latency, like the model inference. They want the newest model as soon as possible. So in this case, we still need to have some trade-off because the network, the bandwidth of network is just there. I think that the fastest way is everyone to fetch data together or something, and they get the newest data. But the thing is, we cannot make it. So which means we need to schedule some data dispatching or something, which means maybe someone have a higher priority, they get the newest data first. But that's based on the throughput of our cluster, and maybe others will come in later, will hit other part of the data or something. So we need to do some rotation, and we need to have some priority list. We cannot make everyone just get the same data. I mean, if you have 10,000 machines, that's very difficult to make it everyone get the same data.
And so my second question, sorry, was that a lot of the stuff that you talked about was data retrieval for training or loading primarily. Do you have a solution sort of for writing in the same way that?
Okay. Let's put it this way. So because I'm the architect of product 3, now we have both read and write. But for the read part, we are more production ready. And we can read is also production ready, but for the read part, it's really got used for so many tech giants, internet companies, and the giant companies. But for the write part, now the write part is still, I think, because for the internet companies, they prefer something more reliable. They can run through us, but we don't provide any acceleration because basically they write something to us. It's not a write back cache. We synchronize the write to the HDFS or to the S3. So there's no performance gain. But we are working on that. We are working on with another, I cannot mention the name, another tech giant. They are using us to store the model and also a checkpoint. They want to have a better throughput. So we give them something called write back cache, which means write to Alexio first, and then Alexio will take care of it. It will stream the data to the under storage later. So it looks like, okay, we finished the write, but actually not. This data is still in the cache. But for that part, it's still ongoing.
Thank you.
Thanks for the presentation. And I just checked out the LSS website, and I saw they have the LSS community version that is based on the open source approach. So for like a beginner, just to recommend us to practice using LSS and how like what should we keep in mind and be careful of the privacy. Is there something we need to like?
Yeah, here's the thing. The version you just check out is the Java version of Alexio. We only have the Java version, but I'm talking about the client, how to use it is still the Java version. The most example is how to integrate with Alexio, with Presto, and the Trino is Java applications. But today, the major use case I share today is more in the machine learning sections. So for here, we may more prefer a Python client, a Python usage. So we are working on that. We will deliver something like a Python package, pip install Alexio, something like that. And then you can have a lightweight Alexio running there. That should be very convenient. It's more convenient. And we will deliver this very soon. One of our internet is working on that. Otherwise, it should be very difficult, It's not our fault. Most open source projects just don't do like this. I think you already suffered from this kind of thing. This is not our fault, for sure. Because I'm also working for the Presto community, the same thing. That's really difficult to set up a running cluster because it's distributed and also you need a lot of settings there. It's really difficult. You may suffer from the first installation. So that's why I mentioned we are working on something like a pip install, which means we can just start a Alexio cluster with one Python command. We are working on that. I think we can deliver it very soon. If you don't want to wait, you can try to install. This is some document. You can try to follow. But I have to say, it's very difficult. You may got a lot of trouble in the middle. Easy. We will do this other as and put it on our website.
Hi. So just in case of a tabular data, we have different kinds of server like OLTP and OLTP, where we store everything on OLTP servers, and on OLAP servers we store just a subset of those which we are really gonna use. So is this similar that you are doing, or is this caching another layer over OLAP servers?
I think that's really a good question. I think that the industry suffered from the issue you just mentioned for more than 10 years. The solution is we are trying to make. I think start from more than 10 years ago. We are trying to do the separation from the compute and the storage, because if you try, I'm talking about the big data area. I'm not talking about the real time. So that's why we have Presto. Which means we make our computer engine to be storage independent. Which means for every query, you fetch the data from the remote. Then we can push a cache in the middle. Am I right? That's the story. That's the story we have 10 years ago. That's why we start our Alexio at that time. But the thing is, it's not quite efficient because all the data, because it's a SQL query sometimes, right? The SQL query, something like a table scan, like a filter, like an aggregation, they love something pre-indexed, pre-compute data. Am I right? So if you are using a database, you always put an index for the column you want to query. But if we're talking about the computer storage separation, it's separated. So, which means it's really difficult to put an index. And also, you can have an index on the remote. It's also really difficult to consume or update or load this kind of index. So, and then some modern MPP, something like Starrocks, like Doris, also like a ClickHouse, they are trying to do some data ingestion. So if you want to query this kind of data, you need to inject the data to the database first. It's more like MySQL. They control the storage. Am I right? This is something different than the Presto. Your Presto, there's no storage. This is storage independent. But for the Starrocks or Doris, you need some data ingestion, which means they put some data on their compute node. Am I right? So for your query, it will just consume the data on their computer, on their compute server. That's the difference. Okay, let's go back to our question. So I think for the Presto case, Presto and Spark case, it's valuable. It's valuable to put the cache in the middle because it's always low data from the remote. But they're talking about Starrocks, talking about Doris, talking about the ClickHouse. They also use their cache, but they don't put the cache at the level of Alexia. They don't put a cache between the remote storage and the compute engine. They put some internal cache for each worker. They cache something in the memory or something in the fast storage for their index, for their data. That's a different. Any other question? No? All good?
All right. Let's give a round of applause for